Welcome to the lecture of ocean acoustics. In this lecture, we are going to discuss about ambient noise in the ocean. The contents covered in this lecture are brief of ocean acoustics, sources of noise, variability of ambient noises, and impacts of sound on marine animals. Ocean acoustics is the study of sound and its behavior in the sea. The field of ocean acoustics provides scientists with the tools needed to quantitatively describe sound in the sea. By measuring the frequency, amplitude, location, and seasonality of sounds in the sea, a great deal can be learned about our oceanic environment and its inhabitants. Hydroacoustic monitoring has allowed scientists to measure global warming, listen to earthquakes and the movement of magma through the sleeve core during major volcanic eruptions, and to record low frequency calls of large whales. As our ocean become more noisy each year, the field of ocean acoustics growing and become more essential. What is ambient noise? The ambient noise is the unwanted background noise. The primary sources of ambient noise can be categorized by the frequency of the sound. Sources of ambient noise. If we take a hydrophone and place it on the seabed for stability and plot the spectrum over a wide frequency range, we could find a number of peculiarities in the shape and the slope of the spectrum. That could be some frequency band where the tonal components occur. And also, there could be a continuous and negative sloping separated by portions where the spectrum could be flat. From the different sources of noise exist and prevalent in different regions of spectrum. The overall frequency range existing over 7 decades of frequencies is divided into 5 frequency band in which the prevailing sources of noise appear to be different. The background sound in the ocean summarized in the graph showing typical sound levels at different frequencies. At different frequencies. The sound levels in this graph are in dB relative to 1 micropascal in 1 Hz wide frequency band. Ultra low band. Almost nothing is known about this noise in this band, except to speculate and to conclude. The measurements mentioned in this graph are in octave bands with the hydrophones at a depth of 300 meter and 1200 meter. The average 300 meters and 1200 meters are included with the measurements in higher frequency band, that is above 1 Hz. The frequency band below 1 Hz are shown here, that is from 0.1 to 1 Hz. It is measured by a pressure sensitive hydrophone and dominated by line components. These components could not actually represent the pressure propagating with the velocity of the sound, but likely to be a part of hydrostatic and hydrodynamic origin. It is interesting to note that the motion of the sea surface produces sound in the air above as well as the water below. Waves in the air with periods near 5 seconds have been observed and attributed in this cause called microbarons. That is nothing but the voice of the sea. Infrasonic band, that is 1 to 20 Hz. This band has a great interest to low frequency passive sonars. During Second World War, data in this band were obtained in connection with new acoustics in order to provide the maximum sensitivity requirements of actuation circuitry. This range of data in 20 dB wide and it's almost higher than modern measurements. In the lowest part of the infrasonic band, in the range of 1 to 5 Hz, the measurement in deep water shows a steep spectral slope of about 10 dB. That is mentioned in this graph. In the frequency range that is 5 to 20 Hz in the ocean areas where ship noise begins to be strong and the measured spectrum level begins to show a reverse slope, suggesting that the emergence of the shipping noise at the upper end of this frequency band. That is, The spectrum reported in this are obtained with the hydrophone located at the mid-Atlantic ridge at the depth of 2,400 meters. The noise was attributed to distant ship traffic, local ship traffic, and the seaquakes as recorded by the seismometers increased by the hydrophone levels above these values for a short period of time. In the absence of ship traffic or in the shallow water, the spectrum the spectrum continues to fall off and to remain dependent on the wind speed over the entire band. And the frequency ambient noise measurement mentioned during the Second World War II, mostly from 2 to 20 kilohertz. From 2 to 20 kilohertz in shallow water, 12 to 110 feet. In the lower part of the infrasonic band, in the range of 1 to 5 Hz, that is represented in this graph. So, from 1 to 5 Hz, the measurements in deep water show a spectral slope of about 10 dB. So, about 10 dB for 1 to 5 Hz. So, about 1 to 5 Hz, at 10 dB of measurement we have, and in the frequency range of 5 to 20, the ship noise begins to be strong and it's in a reverse slope spectrum, suggesting that the shipping noise at the upper end of this frequency band is very strong. So, the hydrophones are located on the mid Atlantic ridge at the depth of 2400 meter. So, hydrophones are located at the depth of 2400 meter. So, this noise was attributed to distant ship traffic or local ship traffic as recorded by nearby seismometers increase the microphone levels above these values for short duration of time. In the absence of ship traffic or in the shallow water, the spectrum continues to fall off and to remain dependent on the wind speed over the entire band. And the second graph, that is figure 2.4, represents the data at 12.5 Hz for 4 locations. That is 12.5, that is at 12.5 Hz for 4 locations. 3 of them are far away and 1 is close to shipping line. A clear wind dependence occurs at a distant site states that the noise will be more when the shipping lane is nearer, because the scarcity of shipping the South Pacific Ocean and is quite more about 15 dB than the frequency about 200 Hz. So the difference between the North Pacific Ocean and South Pacific Ocean are displayed here. In South Pacific Ocean, it's it is to be more quiet that about 15 dB the frequency are less than North Pacific Ocean. A source of difficulty in measurement of infrasonic region is pseudo noise. That is nothing but the self noise resulting the presence of hydrophones. It's stated that there are always currents in the sea, even though in the greater depths the placement of hydrophones in a current results its noise. So one of the impingement of patches of turbulent water carried along the current that create variable pressures when they strike the face of hydrophone. A similar effect is caused by temperature microstructure, which produces a noise through the pyroelectric sensitivity of transducer materials. And the third noise is flow noise, that is caused by the local turbulence and vortex shedding produced by the presence of the hydrophone and its support. Low sonic band, that is 20 to 200 Hz. In these regions where distinct ships are common, this frequency band is distinguished by the noise of distant shipping. The noise in this band still depends on the speed in the place far away from shipping lanes, just like it does for both lower and higher frequency. From this graph, according to Perron, noise spectra were arranged over a 27-day period in January utilizing a non-directional hydrophone situated at 35 miles south of Bermuda and analyzed in one-third octave bands. In the 11th and 17th Hz bands, as well as at higher frequency than 200 Hz, wind-dependent noise can be heard. The non-wind dependent noise with a maximum at 20 and 60 Hz is attributed in a combination of biological sources, shore activity, and far off ocean ship traffic in the region between 20 to 300 Hz. High sonic band. This frequency band was explored during Second World War by a group headed by eminent acoustician V.C. Knudsen. The measurements were made for 14 days near harbors, offshore areas of East and West Coasts, Hawaii, and Great Britain were summarized in a series of curves. And this series of curves were known as Knudsen curves that was published in the year 1948 by Knudsen. The Knudsen curves below 1 kHz indicates that in this region the possible presence of shipping noise and in the absence the change in the slope or reversal of wind slope, that is wind noise in this band represents the measurement. These levels are strongly dependent on wind speed and are slopely, that is slightly less than 20 dB per decade of frequency. The noise intensity falls off slightly less than the inverse square of the frequency. The subsequent measurements tend to show that a flat spectrum for wind noise between 200 and 800 Hz in both deep and shallow water. The data obtained shows that the better correlation with wind speed and with the sea states that wind speed can be more definitely measured than the sea state. And if the noise level is indicator related to wind speed, in certain case that kilohertz frequency, it is possible to use a hydrophone as an anemometer for wind speed measurement at remote underwater locations. Thus, an instrument called NOTAN, that is weather observation through ambient noise, is basically a hydrophone which measures noise at 4.38 and 14.5 kHz. This instrument distinguishes rain noise from wind noise, rain noise being white as the same level with all these frequencies, while wind noise does not. And the last one is ultrasonic band, that is greater than 50 kHz. At frequency from 50 to 200 kHz, depending on the wind speed, thermal noise begins to dominate the noise background. The thermal noise is the noise of molecular bombardment. It is the analog of Nyquist's electrical noise in the radiation resistance of antenna, and it places a limitation on hydrophone sensitivity at high frequencies. The This form of noise was investigated by Mellon, and the thermal noise is mentioned as NL is equal to minus 15 plus 20 log F for the spectrum level in dB. And this expression exploited that since 30 years later, with 3.6% of the expression were obtained by using the experiment method in the laboratory. No measurement work in the real ocean has been done in this frequency range except the measurements at 30 kHz, 90 kHz, and 150 kHz in the ports of California. These locations were found to be extremely noisy and showed greater variability from port to port. From this data, we conclude that thermal noise limit at 30, 90, and 150 kHz is far lower than noise levels prevailing in busy harbors. So, no measurements in this ultrasonic band in deep, quiet open water appear to have been made.